Hi, my name is Christian Meisel. Let me introduce you to the DataScope Select REST API. After a quick overview of DataScope Select, we shall look at a few use cases and then jump into the DSS REST API with a demo of some of its capabilities. We will then wrap up with a list of additional useful resources before moving to the Q&A. Thomson Reuters DataScope Select, or DSS for short, is a hosted delivery platform for non-streaming cross-asset data. Data can be extracted using its graphical user interface and FTP, but everything can also be done using only the REST API. DSS is a mature but constantly evolving product with regular updates to adapt to evolving content and delivery requirements in the marketplace. Today, you need rich financial data to help deliver profitable insights. The quality, relevance, and timeliness of the information empowers you to find new opportunities ahead of your competitors. Thomson Reuters DataScope Select addresses these needs. DSS offers a variety of high-quality, cross-asset, non-streaming, pricing, and reference data, with worldwide coverage, all from a single source. This includes, among others, intraday snapshots, end-of-day data, historical time series, evaluated prices, estimates, terms and conditions, corporate actions, cross-reference data and legal entity data, commodities from Platts, Argus, and other sources, and also news analytics and news stories. New content is regularly added to help you adapt to evolving requirements. The most recent addition is tick history data. Enterprise departments have diverse requirements for financial data. For all these, data coverage must be as complete as possible across all asset types. Data must be of good quality and available in a timely fashion. Data must be easy to access and retrieve at any time. Meeting all these requirements can be challenging, especially when working with multiple data sources. For non-streaming data, DSS meets all these expectations through an easy-to-use RESTful API. Let us look at a few use cases. Mutual funds need to evaluate their holdings daily within strict time limits. This can be done using DSS in a few easy steps: submitting a list of instruments, scheduling an end-of-day data request triggered by data availability, and then retrieving the data to use it in the net asset value calculation. Many mutual funds, including large American ones, use DSS for this. As a side note, there are several possibilities for a trigger by data availability. It can be end-of-day market prices, or you can wait for validated, so corrected end-of-day prices. You can also choose to retrieve corrections separately as a second separate schedule for later delivery. Internet portals typically allow customers to check their portfolio whose valuation requires pricing data. Additional portal features could require instrument reference data, historical pricing, or intraday snapshots. DSS allows such data to be requested on a scheduled basis or on demand. Cross-referencing instruments can be a nightmare, but DSS makes this easy by delivering a rich reference dataset, including support for more than 30 instrument identifier types: RIC, ISIN, CDOL, QZIP, ORG-ID, etc. Another use case is validating existing instrument lists or searching for instruments. Validation helps to filter out bad instrument codes, which could be due to typos, expired contracts, or name changes. DSS also has a search feature which allows searching by instrument code or instrument characteristics. DSS search criteria are quite diverse, and they may depend on the asset class. Criteria such as company name or domicile, currency, exchange, instrument types, strike price, expiration date, underlying, and more can be combined, resulting in powerful search capabilities. So, what is DSS? DSS is a hosted internet service. You can access it from anywhere and there's no need to install anything. The data consumer can be the browser-based graphical user interface, which allows requesting and retrieving data. Optionally, FTP can be used as an alternative mean to retrieve data. Then, there is the API, which can not only replicate the graphical user interface capabilities, but also has additional ones. As a DSS customer, you can use either the graphical user interface or the API, or combine both to optimize your workflow. Data can be extracted using either of two basic mechanisms: scheduled extractions, which occur at predefined moments in time, once-off, or recurring. These can be created using the graphical user interface or the API. On-demand extractions, which occur immediately. These are high-level simplified calls which can only be created using the API. The choice of mechanism depends on the workflow you want to create. These mechanisms are not mutually exclusive. You can use both. For instance, scheduled extractions for data which you require on a regular basis, and on-demand extractions for ad hoc queries. Scheduled extractions are typically used for data requests that are performed regularly. An example could be daily end-of-day data requests. A scheduled extraction requires 5 steps. First, we create and populate an instrument list, which is saved on the DSS server. The list can be created, populated, and modified manually using the graphical user interface. It is also possible to import a CSV file. The list can also be created, populated, and modified using the API. A list is persisted on the server until you decide to delete it. Instruments are validated before being added to a list. In this context, the instrument search tool allows you to find instruments using various criteria, which can be very useful. Then we define a reports template, which is also saved on the DSS server. Reports templates are created by choosing one from a list of available default templates and customizing it by selecting which data field should be part of the returned results. Again, this can be done using either the graphical user interface or the API. Here is the list of currently available reports templates. They correspond to the data landscape we saw at the beginning of the presentation. As you can see, many are available to fit all use cases. We have templates for pricing data, reference data, and a combined one. Then we have templates for analytics, corporate actions, entity data, commodities, estimates, and news. New releases of DSS may include new reports templates. The list of available fields is specific to each reports template. It can be displayed in the graphical user interface or queried through the API. You can include as many of the available fields you want in the template, but for obvious performance reasons, it is best to select only those you require. When analyzing the list of fields for a specific report template, each data field has a description which helps in choosing the right one. In case of doubt, the best method is to select all potential candidate fields during the prototyping phase, then check the results to determine which fields return the data you require, and finalize the field list. This prototyping can easily be done in Postman without coding. This exercise needs only to be done once, as field lists will usually not require changes. After creating the instrument list in report template, the next step is defining an extraction schedule, which is saved on the DSS server. It can be executed one single time or run on a recurring basis. It can be triggered at a specific time or by data availability, like at market close or after data corrections are available. The schedule must refer to an existing instrument list and reports template. Combinations are of course possible. Several schedules can be defined for the same instrument list and the same or differing reports template. We then check the status of the extraction by interrogating the server. Once it has completed, the data can be retrieved. So once it has completed, we can retrieve results from the DSS server. All these operations can be done using the graphical user interface or the API. Some combinations are also possible, like importing an instrument list from a CSV file manually and then referring to it in a schedule created using the API. This allows you to accommodate your use cases in an easy way. Here's the same workflow illustrated by a diagram. The first line is the instrument list creation. The second line illustrates the creation of a customized report template by choosing a default one and selecting the data fields. The third line shows the schedule creation and waiting for the extraction request to be triggered. The last line is for polling the extraction status and retrieving the data. On-demand queries are high-level calls made through the API. They do not have their equivalent in the graphical user interface. We obviously need an instrument list, but this is managed on the client. It is not saved on the server. Instruments can be searched using API calls, so automated workflows can integrate such capabilities. Instead of defining a reports template, the request is made directly, but it specifies a data type which, in fact, refers to a default report template. In fact, here we are covering the previous steps 2 and 3 in one single API call. Even if the mechanism is different, we are referring to the same templates we saw previously. So the request contains the instrument list, refers to a default template, and includes a list of data fields specific to the template. If required, the list of available data fields can be queried using the API, thus facilitating automated workflows. But, as stated before, for performance, it is best to optimize the field list during the prototyping phase. Once the query has been submitted, we check its status by polling the DSS server. Once it has completed, we can retrieve results from the DSS server. Note that nothing is persisted on the server, neither the instrument list nor the custom report template. Now let us talk about the API. There are two versions of the API which currently coexist: the older SOAP version and the newer REST version. A .NET software development kit is available if you want to program in C#, but as it is a REST API, any language can be used. The API is rich and delivers many capabilities. Some mimic what you can do in the graphical user interface. Other capabilities, like on-demand extractions, in other words, on-the-fly requests, are only available in the API. The API is flexible. You can schedule extractions tailored to your needs for anything from one instrument to large sets, selecting the data fields you're interested in, etc. As an example, in the case of embargoes, which occur when you make an intraday request for fee-liable data you are not entitled to, you benefit from automated embargo handling with data delivery based on your predefined preferences. In a nutshell, we recommend you use the REST API. It follows industry standards best practices, is simpler to use, has better performance, and more capabilities. If you have not yet started development, we strongly recommend you go for the REST API. If you already have something developed using SOAP, we recommend you consider migrating to REST. Here are some of the reasons why. SOAP only supports synchronous calls. It might therefore suffer from long calls that are just hanging waiting for results. Long quiescent TCP channels can be disrupted by network rules that limit their duration. The REST API supports asynchronous calls, which allows for a client-controlled disconnect between initiation of an extraction and the collection of the results. Only REST offers API access to existing lists, templates, schedules, and file-based results. This gives you the option of creating them manually and then using them programmatically, which can be quite practical if they hardly change in time. Only REST offers streaming of large results. This does not yet apply to on-demand results, but is currently available for file-based results. The REST API is richer, has a .NET SDK, more API calls, and gives access to more data, like commodities, energy, corporate actions ISO 15022 events, and rig maintenance reports. It also has higher extraction limits and better performance. Now, let us see this in action. Let us start by illustrating how easy it is to play with the API and to become familiar with it. To submit HTTP requests to the API, I will use Postman, a free standalone application available from Internet, but you can use any tool you want. This is a great way to test the API calls, understand the inputs, and see what type of data they deliver before moving to actual coding. Working this way will save you time by reducing your program debugging efforts. For this demo, I'm using a small collection of calls and an associated environment containing some variables. These are subsets of a more complete collection and environment which you can find available for download on the developer portal. First, we need to authenticate to the server with a DSS user and password. To make my life easy, I use some environment variables, where I set the server parameters, and my credentials. I can then use them in my requests. To authenticate, we run an HTTP POST request to the authentication request token endpoint. The HTTP body must contain a credentials request and associated parameters. In other words, my DSS server username and password, which are the same as for the graphical user interface. The HTTP header specifies that the content type is JSON. Let us run it. The response content is JSON. The body contains my authentication token, valid 24 hours, which I must add to the header of all my API requests. For ease of use, I copy it to another environment variable. In the bank portal use case I mentioned before, we needed end-of-day data. Let us see how we can extract that data on demand. The HTTP header of our request now has one added field, for the authorization token we just retrieved. The endpoint is now that for data extraction. The HTTP body contains the details of our extraction request. It specifies several things. The type of data we want. The type of data refers to a default template, of which there are many to choose from, as we saw previously. As this is an on-demand request, the custom template will not be persisted on the server. In this case, we select end-of-day parsing. Then there's a list of content field names. Many content fields are available, and you can specify those you want for each query, therefore optimizing the whole process. To find out which fields are available, there is an API call to a specific endpoint to get valid content field types for a particular report template type, in this case, end-of-day parsing. As you can see, there are hundreds of available fields. The field list is specific to the report template. We could take all fields automatically from the output of this API call by pulling out all field names and reusing them in the extraction request. That said, it is much better to optimize the amount of data by reducing the set of fields. You could filter them programmatically based on their name, but it is easier and more efficient to simply select them manually, as this is a once-off operation. This can be done in the prototyping phase, using Postman as a testing tool without coding. First, Make an initial selection of all potential candidate fields that might fit the data you want to retrieve based on their name and description. Then execute the requests for that list of fields in Postman. Check the return results to determine which fields return the data you really require. This will allow you to finalize a field list. You only need to do this simple exercise once, as field lists will usually not require changes. There are great benefits in this. It leads to smaller datasets to extract and handle, much faster query execution and data delivery, and a lower burden on the servers, network, and your processing. As a result, your entire workflow will be much more efficient. Finally, there's a list of instrument identifiers. Note how we can use different identifier types. In this case, we have a QZIP and a RIC. Well, right now I only want one instrument, so let us just delete the other one from the list. I have just launched the extraction request. The extraction time depends on the server load and on the amount of data we requested. So, in other words, the number of instruments and data fields. Here are the results with yesterday's end-of-day prices. In the bank portal use case, we might also want a time series of historical end-of-day data. Let us see how to retrieve that. Like in the previous call, we use the extraction endpoint. The HTTP header is the same for all API calls. The HTTP body contains the extraction request. This time, the data type is a time series. This is again a reference to a default template, as we saw previously. Again, we define a list of content field names, a list of instrument identifiers, and now a few conditions, including the time frame for the time series. Here we set it to 1 business week. Here are the results, with a series of end-of-day prices, one data record for every single day. In the bank portal use case, we might also want a snapshot of the current price. The extraction request is easy to understand now that we've seen the other ones. This is an intraday pricing request with a set of fields, instruments, and conditions. This is a bit of a special case. Intraday data is fee liable by exchange, so obviously your account needs the appropriate permissions to access this data. Now, if you do not have those permissions, then the embargo mechanism will automatically manage this and delay delivery of the data. Automated embargo handling is a great feature, but fairly complex and out of scope for this demo. If you are interested in this topic, check out the 4th DSS.NET tutorial on the portal. It explains embargoes in great detail. As my account is permissioned for intraday data for this exchange, I got my results immediately. Here they are. All API calls can be tested in this easy and quick way to understand the inputs and outputs. Now, what does this look like when you start programming your own project? Let us start with C#, using the .NET SDK available for DSS. The SDK is a wrapper around the REST API calls. It manages the HTTP communication and JSON content for you. In this demo, I shall use some of our tutorials code. I will not show its installation. It is very easy, and it's described in detail on the developer portal. All that is actually required is to download the SDK and the tutorials code and copy them to your own machine. You remember that in the mutual fund use case I mentioned previously, we needed to schedule regular extractions of validated end-of-day data as soon as it was available, as time was quite critical for this use case. Let us see how to do that in C# using the DSS.NET SDK. Here are the steps we will see in this code sample, which illustrates setting up a scheduled extraction. They mimic what can be done in the graphical user interface. After authenticating to the server, we will create an instrument list, a report template, and a couple of schedules. All of these will be persisted on the server until we decide to delete them. We will not cover checking the schedule status and data retrieval. We will see that in a different sample. For our program, we decided to create a separate class dedicated to DSS-related methods. This is not obligatory, of course, but this is how we wanted to structure our program. As a first step, we need to include the required SDK libraries. The most important code here is that for creating an extractions context, using as parameters the DSS URI and our user account. The extractions context is the starting point for most of the API methods. It is the foundation element of all our code. Actually, you can also create an additional context for searches, but in this example we don't need it. All following API calls in this example will refer to the extraction context. In our main program, after the required include statements, we define our user account, and we call the method I just showed you to create the extraction context and log in to the DSS server. Then we expose the extractions context. After that, we can start using the API calls to request data. In this first example, we will mimic what can also be done manually in the graphical user interface. So if you're familiar with the GUI, you will find this really very simple. To request data, there are 3 steps. The first one is creating and populating an instrument list. The second one is creating a report template. The third one is scheduling the extraction. Once the extraction has run, the data can be retrieved. All this is done using the API. Our first step is to create and populate an instrument list. We first create an array of instrument identifiers. Like what we saw in Postman, each identifier has a type, and they can be different. A user-defined tag can also be added. That is optional. As a side comment, note that this code is very simple and not productized. This is to facilitate the learning progress so that we can just read through the code. But you will find more complex samples in the downloads we provide. Next, we create an instrument list on the DSS server, using an API call that refers to the extraction context we just created. The list is initially empty. We therefore populate it by appending the array of instrument identifiers to our instrument list. A whole set of API calls are available to manage the instrument lists, create, edit, and delete them. The second step is to define a report template, in this case for end-of-day data, as we can see here. We define its name, the output format, CSV, and the set of data fields we're interested in. Again, as we saw in Postman and in the slides, we are making a choice of a default report template and customizing it by selecting a subset of all the available fields. Finally, we proceed to the actual report template creation on the DSS server. The third step is to create the extraction schedule. In this demo sample, we even create 2. Let us start with a single immediate data extraction. If we run it during market open, it will deliver end-of-day data for the previous day. If we run it after market close, when end-of-day data is available, then it will deliver data for today. See how we define the extraction schedule's name, set it to run a single time, and this is to be triggered immediately. We refer to the instrument list and report template we just created, and define the output file name. After defining the schedule, we create it on the DSS server. Our second example schedule is for recurring extractions, triggered by data availability. This is what we needed for the mutual fund use case. Here we define the schedule's name, our time zone, the days on which it should run, and the data availability trigger, which in this case will deliver only today's data, wait for data corrections, and deliver the entire dataset. We can decide to set a time limit on this wait period to ensure we get data before a specific timeout. Here we set it to 2 hours. Again, we refer to the instrument list and report template and define an output file name. All this before creating the schedule on the DSS server. As you have just seen, several extraction schedules can be defined using the same instrument list and report template. The system is very flexible and the options quite powerful. You can define as many instrument lists and report templates as you like, link them to various schedules, etc. For our particular case here, if we wanted to, we could, for instance, schedule a first end-of-day extraction that would occur as soon as data is available, without waiting for the corrections, and a second one that would trigger later, containing only the corrections, for instance. We shall not run this extraction now, as we cannot afford to wait till the end of the day. So let us move on to see instrument cross-referencing, another one of our use cases, and run an actual data extraction. Here's the workflow for our second example of C# code, which is for an on-demand request. On-demand calls are simplified high-level calls that do not exist in the graphical user interface. This is where you can start leveraging the advantages of the DSS API. With the on-demand calls, we do not create an instrument list or report template on the DSS server. We proceed to the data extraction directly. The workflow of our program is the following. After authenticating to the server, we will first create an instrument list, locally, not on the server, and a field list, also local. Again, the field list will be specific to the type of data we are requesting, which in this case is terms and conditions data. We chose this template because it is one of those that deliver instrument codes, which is what we need to cross-reference. Then we will create and run our on-demand request, and finally retrieve the results. Let us look at the code. In the code sample, we shall concentrate on the API calls. First, we authenticate to the server. We create an array of instrument identifiers and another array of field names we want to retrieve, just like in the previous example. As we are cross-referencing, our field list contains mainly the set of instrument identifier types we're interested in. Here we used 5, but more than 30 are available. We also added the currency, just for the fun of it. We then create and run a terms and conditions extraction, using our 2 local arrays. Once the call has been made and the extraction has completed, we can treat the results, which are returned as data rows, 1 per input instrument. First, we shall extract the data field names, then the values. Here we see how we extract the field names. After some basic error checking, we take the first row of data and retrieve the field names from the dynamic properties keys of this first row of results. Now to the actual data values. Here we loop through all returned data rows to extract the data from the dynamic properties keys. In this sample, we simply print them out. Let us run the sample to see this in action. Here's our authentication token. Here's the list of return field names, which corresponds to what we requested, quite obviously, and the data containing the cross-referencing results and the currency code. This simple example demonstrated that retrieving data from DSS is very quick and simple to program. Okay, to end this presentation, let us look at programming in other languages, for which there is no available SDK. As an example, I'll take Java, but what we will see now can be applied to any language that supports HTTP request response and JSON handling. All the sample codes you see here are also available for download from our portal. Let us illustrate another use case, an instrument search. Searches can be used to validate existing instrument lists or to find instruments that correspond to specific criteria. This is what we shall do here by searching for a future, using as criteria the strike price, maturity date, and underlying. As you can see, other search examples are delivered in the set of samples. In Postman, where we do our initial API calls testing, the request looks like this. So, how can we do the same in Java? Here are the steps we will see in this Java code sample. After authenticating to the server, we will create an on-demand search request and display the results. We start by importing some public domain libraries for HTTP requests and for JSON handling. In C#, this was done by the SDK, but in other languages you must do it yourself. There are other libraries that fulfill the same purpose. These were chosen just because they are popular. There are many includes because the authors of these libraries decided to sort the methods in several classes instead of putting them all in the same one. Feel free to use the libraries of your choice. Here's the main, where we see there are just two calls, one to authenticate and the other for the search request. Let us start with the search request. Here's how the search request is created. We create an HTTP post using the appropriate URL, which includes the endpoint for futures and options searches. Let me display the same request in Postman and in Java simultaneously, so we can compare them. Here we have the header fields in Postman. See how they're implemented in the Java code. The session token was retrieved in an earlier part of the Java code, also using an HTTP request. We will look at that briefly afterwards. But right now, let's look at how we define the request body. Here you see the HTTP body in Postman. And here's how we create the same in Java. I made an attempt to make these visually similar, to make it easier for you to understand how what was tested in Postman can then easily be implemented in Java or any other programming languages. In Java, we use a JSON-ordered object. We define the search parameters as required and leave out those we do not need. You also see how we can make range or value comparisons, this on numbers or on dates. Here we use that to define a range for the strike price, and we use a comparison for the maturity or expiration date to be in 2017 or later. For some parameters, it is possible to use a wildcard, like here in the identifier. The JSON object is converted to a string entity, which is required for the HTTP POST request. We define a response handler, and then we execute the request. Finally, we just print out the returned JSON data. The request for the session token was made in the same way, as you can see here. Let us run the program in Java. We see the token, the request, and the response. Let us run the same request now in Postman. Well, as expected, we get the same results in Java and Postman. Let us now conclude. So, how can you move forward? The developer portal hosts many resources, an API overview, a quick start to get you on track in no time, documents, downloads, many tutorials, links, and an active forum for questions and answers. The downloads include a variety of sample code in several programming languages, including all those you have just seen for Postman, C#, and Java. Also available in downloads is an example application delivered with its source code. Written in C#, it demonstrates many of the API features through working calls. Not only does it allow copying C# code to your own application, it also displays the HTTP requests and responses, which is very useful if you are programming in a different language. The DSS website hosts not only the graphical user interface, but more material to help you, including a browsable API reference tree. Thank you for following this presentation, which would not have been possible without the excellent knowledge and support of many colleagues in the DSS group. Many thanks go to them. Now we will move over to the Q&A session.